Thank you very much. And thank you to everyone for coming back for lunch. And I'm delighted to be here. It's actually my first visit to Uganda. It's been a real pleasure. So it's been great to hear the excellent science from all of Thrive Fellows. So I'm talking about epidemiology and control of epidemic meningitis in Africa. Now, this area in the dark orange, really surrounded the countries affected in yellow, is known as the African meningitis belt. First described by General MESAU-MEPI in the 1960s. And this area is characterised by high incidence of meningitis, which occur, and outbreaks occur in the dry season. There's a climatic risk element to this. These are very dry areas, and epidemics occur at the time of year when it is very dry and dusty. And there's probably some physiological mechanism to do with the dust. The dust is causing some damage to people's throats, making it making it easier for the bacteria to invade. So the main culprit is this bug in the top corner. This is Nigeria Niger. Lots of different bacteria and viruses can cause meningitis, which is sort of inflammation of the brain, the meninges of the lining of the brain. But epidemic meningitis tends to be caused by Nigeria Niger. It's surrounded by this sugar capsule, and that's relevant because there are different types of capsule. And group A is historically been most common in Africa, and groups B and C are more common in Europe and other parts of the world. So the incidence is really strikingly high and occurs, as I said, in epidemics. So this is a long time series from Chad, and you can see these peaks in disease incidence occurring irregularly but fairly frequently. Some years you may have a big epidemic and then it disappears, and other years you may have sort of epidemics in consecutive years. And as I mentioned, it's really an extreme example of a seasonal disease and also an epidemic disease. This behaviour is actually quite difficult to explain, but I'll make some attempts in doing that. So since we're in Uganda, if you remember the previous map, really, that Uganda, Tanzania and Kenya really on the very edge of the meningitis belt. In Uganda, outbreaks are infrequent. The last major outbreak was in Arua district in West Nile in 2007-8. And by meningitis standards, this isn't an enormous outbreak, but 380 cases and a considerable number of deaths, because the case fatality rate is still about 10%, even with effective antibiotic treatment. Some areas of Uganda have more recent experience of Group W, but to a lower extent. And the World Health Organization considers the 36 northern and 3 western region districts to be at risk of meningitis outbreaks. It's really limited to particular geographies in Uganda. Kenya also has some districts at risk, and Tanzania probably less so, being further away from the belt. So, going back in time a bit further to 1996-97, it was the largest ever epidemic wave across the meningitis belt, concentrated in northern Nigeria. But there were 250,000 cases of meningitis and 25,000 deaths. And this is probably an underestimate because the surveillance systems break down at this level, the health systems break down at this level, but really this was catastrophic. The tragedy was that there had been earlier vaccine trials of an A+C conjugate vaccine. And a conjugate vaccine consists of this outer sugar coat of the bacteria attached to an immunogenic protein, in this case tetanus toxoid. And in the Gambia there had been trials in 1992-93 of an A+C conjugate vaccine, which would have been perfect for targeting outbreaks in Africa and outbreaks of Group C disease elsewhere in the world. In the UK, around a similar time, the number of cases of Group C disease began to increase. And at its peak there were about 1,000 cases of meningitis in the UK. So nowhere near the scale of this problem, but unfortunately, because of the market forces, the drug companies pressed on with a single monovalent C vaccine, and no one was interested in making a Group A vaccine. Until the Bill and Melinda Gates Foundation stepped in to develop a really novel project, the meningitis vaccine project, which was established in 2001 as a virtual vaccine company, really, to try and bring all the pieces together. We knew it was achievable to make conjugate vaccines, an MVP wanted to do this and make an affordable vaccine for African populations. And it really is a fantastic story. They targeted just Group A, because that was responsible for most epidemics in Africa. They had a very rigorous clinical development programme. It was actually quite quick. The Ebola vaccine trial make it seem quite slow now, but within 9 years they've gone from inception to having a fully licensed product. And this vaccine was made in India, the Serum Institute of India, for 40 cents a dose. I remember the director of MVP saying at the beginning, when he was consulting with African ministers of health, he said, don't make us a vaccine we can't afford. The key thing for this vaccine has to be cheap, has to be affordable. So they went in with a target price of 50 cents a dose and actually sold the first dose for 40 cents, which is quite incredible. In comparison, the C monovalent vaccine list price is about £25. So again, really different scale. The vaccine was ready in 2010 and was introduced first in Burkina Faso, mass campaigns of 1 to 29-year-olds. Burkina Faso immunised 10 million people in 10 days. That's also pretty impressive to me. The vaccine was then rolled out across the meningitis belt over several years, and in fact, Uganda's campaign was in 2017, so this timeline spread out a bit. But I think to date, nearly 300 million people have received this vaccine. So quite incredible efforts. As the vaccine was being developed, recognised that this would need to be supported by research efforts. Hiding in that picture somewhere is Professor Brian Greenwood from the London School of Hygiene and Tropical Medicine, and I'm sure many of you know. And he led the African Meningococcal Carriage Consortium, bringing together partners from 7 different African countries to really study the epidemiology of meningococcal disease in Carriage. It was a great group to work with, fantastic, one of my sort of earliest experiences of really working with African partners, and it was really a great project, and everyone worked fantastically hard, and I'll tell you how many the sort of work we did. But why is it the Carriage Consortium? It's not the Meningitis Consortium, it's the Carriage Consortium. And the reason for this is that disease is really the tip of the iceberg for meningitis. The bacteria carry the backs of people's throats and circulate asymptomatically. So if you only look at disease, you're missing nearly all the transmission. This was particularly important for conjugate vaccines. The older polysaccharide vaccines could stop this part, they could protect people against disease. The newer conjugate vaccines could also prevent these cycles of transmission, they could stop people carrying. And this has enormous benefits for herd immunity, so you get much more bang for your buck with this new improved conjugate vaccine. So we wanted to study the vaccine's effect on carriage and understand more about the patterns of carriage across the belt. So how do we do this? And this is a picture from Chad of someone being swabbed, a quick cotton-tipped swab, reaching to the back of the throat, sweeping over the uvula and one of the tonsils, and then you plate out the bacteria on agar plates. And then some of the teams were getting up to 100 swabs a day to process in the lab. So there were lots of work involved in this. I love the tongue sticking out as a helpful indicator. It was helping this child having the swab. So what did we find from these carriage surveys? I mean, it wasn't that we didn't know anything about carriage. Professor Greenwood and I did a review of all the data that there was on carriage, which sort of dated back to the 1960s, and there's been quite a few studies, but what they showed was that the prevalence was really, really variable over time. The serogroups were really, really variable. We weren't sure, is this true? Had people just been using different methods, and that's why we get different results? And this was a way, MenAfricar was a way of using a standardised protocol. Everyone was using the same lab methods, the same swabbing technique, so we could really get to grips with whether the variation that had previously observed was true, whether it was an artefact. So there were 48,000 swabs at least taken during 3 cross-sectional surveys conducted between 2010 and 2012 across the 7 countries, although Nigeria struggled because of the location, which was in Maiduguri, so for security reasons that site couldn't continue. But across the other sites, between 2,000 and 5,000 swabs were collected in each survey. So really major efforts, and the teams all did fantastically well. And what we were able to show is that actually prevalence varies by location. And even within the same location, carriage prevalence also varies. You'll notice in Senegal, carriage is quite low. The first 2 surveys running about 3%, and then by the 3rd survey, it hits 20% as a new strain is introduced and becomes established in the population. So while the overall carriage rate was about 3.5%, there was really substantial variation. Another study in Burkina Faso also had a reasonably consistent picture of this, overall about 3%, but quite variable. Now, for sort of an epidemic disease, this low-level background was a bit puzzling. I think it probably makes sense if you think about it as an immunising infection, and that strains, there's no sort of stable background of carriage, so particular strains can and do sometimes take off, and then that is a potential signal for an epidemic if that strain is particularly pathogenic. Another clue is gained by looking at the diversity of the strains over time. It's probably a bit hard to see this graph, but the colours represent the different strain types. The first thing to point out in this graph was actually one of the aspects of the study was to evaluate the effect of the Group A vaccine on Group A carriage, and we couldn't find any Group A carriers. We only found them in Chad. So this red pie at the top, we only find the carriers in Chad. And this was a real puzzle because we knew that there was Group A disease, but Chad in particular was experiencing elevated levels of Group A disease. And similar to what you might see for type 1 pneumococcus, in that you see the bugs in disease, but not necessarily in carriage. So Chad was the only place to find Group A. Another place is there was a diversity of strains that we found. And in particularly interesting was that Senegal and Ethiopia, on the edges of the belt, where actually disease risk is lower than countries like Burkina Faso, Niger, and Mali, had a much greater diversity of strains. So probably there's more diversity, and therefore there's a more stable background of different strains in these locations, which might mitigate the epidemic risk. So what else did we find in the MENAfricar study as well? Brilliantly, we showed that the vaccine works. It's highly, highly effective. I mentioned that Chad was experiencing Group A disease, and we in fact had the chance to do an amazing natural experiment. There was insufficient vaccine to target the whole country at once, as had been done in Burkina Faso. So the area in red was first targeted with the vaccine, and then later on the area in blue. So in 2012, the year after the area of the capital had been immunised, we could see cases, the Group A meningitis disappear in Chad, whereas in the unvaccinated areas they continue. And so we had very high vaccine effectiveness. So this is great, we know the vaccine protects against disease, but what was it doing against carriage? Because this is when all these amazing herd effects can kick in. And in fact, we also showed the vaccine was highly protective against carriage. Like I said, we didn't find many Group A carriers, but we found enough to show this effect. There was a 98% difference in the carriage prevalence before and after vaccination. So what we could then expect from that would be a long-lasting protective effect from this vaccine, not only because of the direct protection, but also because of the indirect protection or herd immunity. So in Chad this was shown, and then following on from this, as the vaccine was rolled out, we could analyse the vaccine's effect in 9 different countries who had consistent and reasonably good surveillance. Now, the surveillance of meningitis is based on a suspected case definition, which is not very specific. So what we found is that there was about a 60% reduction in suspected cases of meningitis post-vaccination, and there was a 60% reduction in outbreaks of meningitis, so reaching an incidence threshold of 10 per 100,000 in a week. It's a pretty high incidence. And so the vaccine was clearly working well. Why only 60%? You might expect more. I mean, we did see a greater effect on the specific laboratory diagnosed Group A cases, which declined by more than 99%, but only a fraction of cases have a lab report. So the rest of the cases of meningitis that were being picked up might have been caused by other groups, might have been caused by other bacteria, such as Streptococcus pneumoniae, or they perhaps weren't true cases of meningitis. And efforts are ongoing to really strengthen the surveillance across the belt. But the headline figure of 60% reduction in the disease burden I guess is still pretty impressive. So what questions were remaining? I mean, the vaccine's working, this is brilliant. But the vaccine was being used in these mass campaigns. Everyone aged 1 to 29 was targeted in these massive campaigns. Very well accepted, coverage was very high, of the order of 90% or more. Actually, I'm sure there's some administrative coverage that I've seen that's 120%. So people really did want this vaccine. But the questions are remaining, what do we do in the long term? How do we sustain these impressive levels of protection? And to really try and work that out, we developed a range of mathematical models. So it wasn't possible to go and test lots of different long-term strategies in clinical trials because, well, the short-term effects of the campaigns had wiped out the disease. And also it would be a major effort to do several clinical trials with lots of different strategies. So one way of addressing these questions is to make a computer model and simulate the effects of different vaccine strategies. And this is what we did here. It's a fairly standard technique where you compartmentalise people into different categories. So they could be susceptible, they could be a carrier, they could have disease, or they could be immune. And there's an equivalent category for people who are vaccinated. If you're vaccinated, you have a lower chance of being a carrier and a lower chance of getting disease. So we could simulate lots of different vaccine strategies to see what was going to be the best thing to do in the long term. So the World Health Organization is keen on strengthening the routine immunisation platform, so that was one of the options, to have a routine immunisation between 9 and 18 months of age. Another option was to look at periodic campaigns, so every 5 years you go back in and target everyone under 5. If you had no long-term strategy, this was bad news, because what you get would be a long honeymoon period and then disease would resurge. And the final strategy was a combination, so you might wait 5 years after your initial campaign, introduce into routine EPI, and have a catch-up for everyone who missed out on the vaccine. So it's quite useful to compare these different strategies. What I'm not showing here is some trade-off between the periodic campaigns and the routine immunisation. So if routine EPI coverage is less than 60%, you might be better off doing a campaign. And it was interesting to see how this scientific paper we wrote was translated for policymakers, and PATH made this slide. It is the figure that we produced, but they changed it to really emphasise that if you had no long-term campaign, the risk of resurgence of meningitis. So you can see the red line, to have a long honeymoon period of 10 to 15 years, and then disease will come back if you do nothing. So this is a strong message that there needs to be a long-term vaccination strategy. And this was adopted as WHO policy, together with results from clinical trials that showed that the vaccine was safe and effective in toddlers, children aged 9 to 18 months. This is all good news. This is all brilliant. There's a vaccine. It's affordable. It works brilliantly. Disease burdens declined, and there's a long-term plan. This is a fantastic public health story. Is that the end of the story? Well, sadly not quite. The eagle-eyed of you may have noticed on one of my figures that although the cases of group A disease plummeted to virtually 0, there was another line that went the opposite direction. And in fact, they were cases of disease caused by other meningococcal serogroups. And in 2013, before these districts in Nigeria were vaccinated, a new group C strain emerged that MENAfricar could not protect against, and that there was no affordable vaccine at that time that could offer long-term protection. So following the emergence in 2013 and 2014, there was a big epidemic in Niger in 2015, followed by a quiet year in 2016, and then in northern Nigeria in 2017, there were over 15,000 cases of Group C. So obviously more public health action needs to be taken to combat this, and more research and interesting research questions that come up. So one of the things we need to look at as well, how can we build a vaccine stockpile for reactive vaccination? How many doses might be needed for that stockpile? What's the ongoing risk, which is incredibly difficult to predict actually, because it's a very unpredictable disease. So one way of trying to get to grips with that a little bit better was to map out the spatial and temporal spread of this new strain. So you can see the little red dot in 2013 where it emerged in Nigeria, and the spread slowly at first, and then 2015 outbreak in Niger. 2016 fairly quiet yet, but the bugs are obviously still circulating, and then 2017 a larger epidemic in Nigeria. 2018 and 2019 have also been fairly quiet years, thankfully, but you can see this sort of spread across and down, which indicates that perhaps the strain is now circulating more widely and there's still a high risk. One of the things we did as well to look at, could we improve the current reactive vaccination strategies, for example, by targeting neighbours of affected districts, not just the affected districts themselves. But in better news, Serum Institute of India is also developing a multivalent conjugate vaccine, which would cover A, C, W, Y, and X, which is about all the strains of meningococcal disease that have ever been found to cause disease in Africa. And this will also be, hopefully, an affordable price, but not as inexpensive as the MENAfricar, because it's a more complicated vaccine. Gavi were interested in supporting this vaccine, and my team were involved in modelling different declensions and seeing whether this vaccine would meet Gavi's vaccine investment criteria. And thankfully in December last year, Gavi decided that it would like to support this new meningitis vaccine once it's developed. So potentially we can see an end to all meningococcal meningitis epidemics in the meningitis belt. One of the key questions that Gavi wanted to know is, well, do we really have to vaccinate everyone aged 1 to 29? That's a big population. Can we squeeze this group? And in fact, the risk of meningitis is pretty flat, mainly affecting children and young adults, but probably the 20 to 29-year-old group are not the key transmitters, and they have a lower incidence. So potentially you're already squeezed a third from that target group. And the other thing we looked at was these patterns of carriage. So is there a particular group that are driving transmission of these bugs across the population? And these curves are from a systematic review and meta-analysis of African carriage studies, and they're quite different to similar studies we've done in Europe. The curve's flatter, it's not quite as peaky, and the peak age of carriage is earlier, around 10 years of age. You wouldn't expect it to be the same as in Europe, but this is interesting because that tells you, well, maybe we need to concentrate efforts around age 10. An interesting thought about how we might combine this with a HPV vaccine platform. So just to wrap up, there's lots of, as I mentioned at the start, there's lots of different causes of meningitis, not just meningococcal meningitis, and it occurs around the world. So similar to the Malaria Action Plan, the World Health Organization are also developing a roadmap to defeat meningitis by 2030. And this is the 4 main types of bacterial meningitis, but also because some of the pillars affect advocacy and awareness of symptoms and support for survivors of meningitis, they will apply more broadly. So there'll be a big consultation in September to try and get everyone to buy into this meningitis roadmap and hopefully see these ambitious targets being reached by 2030. With at least a 90% reduction in bacterial meningitis. So to wrap up there, hopefully I've shown you that MenAfricar, a tailor-made vaccine for Africa, has been a major public health success. Research efforts have helped to understand the vaccine effectiveness, how it's working, and to guide policy. But there's a remaining threat from other supergroups and other bacteria, which hopefully will be addressed by this roadmap to defeating meningitis by 2030. So thank you very much for having me. Thanks to my hard-working students and the MenAfricar team and people who sponsored this research.